Hi students, welcome to this video. This video explains the basic concepts on capacitors, the properties, the construction and different types of capacitors will be discussed in this video. And finally, we will see how a variable capacitor is made. So let's begin with some of the basics of capacitors. A capacitor stores electrical energy in the form of electric field. The unit of capacitance is farad and we use the letter F to represent farad. The value of capacitance will be usually of the order of microfarads. The capacitance in the magnitude of farad is very rare, so mostly we will be having capacitors with the capacitance in the order of microfarads. A capacitor consists of two conducting plates separated by an insulating medium. So we usually use metallic plates and a dielectric material in between the plates. A capacitor can be charged by connecting it to a battery. So a capacitor will be charged fully if we keep the battery connected to it for a very long time. And finally, the capacitor attains a voltage which is equal to the voltage of the battery. Then we will say the capacitor is charged fully. During the charging process, a current flows into a capacitor, and when it is charged fully, the current stops. Also, during the charging process, a charge of the amount of Q is moved from one plate to the other. So one plate has charge plus Q and the other has minus Q. So the net charge on the capacitor is 0 at charged state as well as at uncharged state. We know that if a capacitor is uncharged, then there is no charge inside it. And even if a capacitor is charged, the net charge on the capacitor will be 0 since one plate is having positive Q and the other is having negative Q. Now we will see the symbol of capacitor. So we use this symbol when we draw a capacitor in a circuit. So this one is the symbol of a fixed capacitor. For a fixed capacitor, its value is always a constant. We cannot change its value according to our need. And this one is a polarized capacitor. So for a polarized capacitor, it is having a positive plate and negative plate. So we have to take care while we connect this capacitor in a circuit. We have to consider the polarities of the capacitor. We cannot connect this capacitor as we connect our ordinary capacitors. For ordinary capacitors, we can connect any terminals on any side. But here, for a polarized capacitor, we have to connect the positive and negative terminals according to the positive and negative side of the voltage in the circuit. If we connect differently, it may damage the capacitor. And this symbol is that of a variable capacitor, and a variable capacitor means its capacitance can be varied. And here in this diagram, we are showing the architecture of a capacitor. We can see the two metallic plates, and in between you can see a dielectric material, and two terminals are taken from the metallic plates for the connection purpose. Here also you can see a capacitor which is having two metallic plates and a dielectric in between them. A parallel plate capacitor has two metallic plates which are parallel to each other, and usually both the plates will be having the same area A. So if we have a capacitor with its metallic plates having area A, and the plates are separated by a distance d, then we can write the equation for capacitance of such a capacitor as C equal to epsilon A by D. Here epsilon is the dielectric constant of the material used in between the plates, and A is the area of one plate, and D is the distance between the plates, or it can be the thickness of the dielectric material also. In a capacitor, the metallic plates are separated by an insulating material which is usually called a dielectric. What is a dielectric? It's an insulating material that can be polarized by applying an electric field. The dielectric constant of a material is also called the permittivity. It represents the ability of a material to concentrate the electrostatic lines of flux. In other terms, the dielectric permittivity represents the ability of a material to store electrical energy in the presence of an electric field. All materials, including vacuum, store energy when placed in an electric field. The permittivity of vacuum is defined as the constant epsilon 0, which is having a value equal to 8.854 into 10 raised to minus 12 farads per meter. And here are a few examples for dielectric materials which are commonly used for capacitors. These materials have different dielectric constant or dielectric permittivity. So the examples are paper, mica, glass, tantalum oxide, polyester PT, aluminum oxide. These are commonly used dielectric materials. Now we will see the amount of charge stored in a capacitor with capacitance C. So when we charge a capacitor to a potential V, then that capacitor contains charge equal to C into V. So Q equal to CV is the equation which represents the amount of charge stored in a capacitor with capacitance C when it is charged to a voltage V. The resistance offered by a capacitor is known as reactance, and that reactance is represented by Xc, where that C indicates that it is the reactance of a capacitor. And the reactance is similar to resistance, but there are differences. Reactance also opposes current through the circuit, but the main difference is that the reactance is a frequency dependent quantity. We know that the resistance of a resistor is a constant. It remains a constant for all the frequencies of the signal which is flowing through it. But for a capacitor, its resistance is not a constant. It varies with the frequency of the signal flowing through it. So we will use a different term to show its resistance, and it is reactance. And we have an equation here for the reactance of a capacitor, Xc equal to 1 by omega C, and we know that omega is equal to 2 pi f. So we can write this equation as Xc equal to 1 by 2 pi Fc. Now what about the reactance of this capacitor to a DC signal? We know that the frequency of a DC signal is 0. So if we substitute that 0 here for this F, we will get reactance is equal to 1 by 0, or it is infinity. What does it mean? If the capacitor is having infinite reactance to a DC signal, it means the capacitor does not allow the flow of DC current through it, or a capacitor acts as an open circuit to a DC signal. It will never allow DC current to pass through. Now what about the reactance of this capacitor to a AC signal? For an AC signal, it is having a frequency, So depending on the frequency of the signal, the reactance varies according to this equation. So from this equation it is clear that if the AC signal is having small frequency, the capacitor will be having very large reactance. So small frequency signals will not be easily allowed to flow through a capacitor. And if an AC signal is having very high frequency, then we can see here that the reactance of the capacitor will be small. So very large frequency AC signals will be flowing through a capacitor very smoothly without much reactance. Now we are going to see different types of fixed value capacitors. The first one is Mica capacitor. Here the dielectric material used is mica, and you can see the metallic plates here, two metallic plates. In order to increase the area of the plate, we are using this method. Different layers of metallic plates are used and they are connected together to form one plate of the capacitor. So both the plates are arranged in layers. That will help us to increase the area of the plate. And in between these plates we can see here the mica is used as dielectric. Now this is ceramic capacitor. It consists of a ceramic disc, and on either side of that disc metals like copper or silver is coated. So we have a ceramic disc on either side of which a metallic coating is made, and these coatings act as two plates of the capacitor, and the ceramic disc acts as a dielectric. And we will take tinned wire leads outside from the metallic coatings for the connection purpose, and the entire unit is coated with plastic. What we see here now is a paper capacitor. It is made up of two metallic plates, and we use paper as the dielectric material. We will place the paper in between two metallic foils so that we can roll them, and by doing this type of rolling we can increase the area of the plates. At the same time we can reduce the total volume. So capacitor will be seen small, but inside it there is a very large plate area. So this method of rolling of metal foils will help us to achieve very large plate area in a small volume. So this will help us to increase the capacitance of the capacitor also. Here you can see electrolytic capacitors. It has an aluminum foil with aluminum oxide film on one side. So it's an aluminum foil and one side is coated with aluminum oxide film. This aluminum plate acts as the positive plate and the oxide as the dielectric. And this oxide side is in contact with a paper which is fully soaked with an electrolyte, and it is almost saturated with that electrolyte. This electrolyte acts as the negative plate of the capacitor. So for an electrolytic capacitor we have an aluminum foil with one side of which is aluminum oxide film. So the plate acts as the positive plate of the capacitor and the oxide layer acts as the dielectric, and in contact with the oxide layer we keep a paper soaked in electrolyte, and the electrolyte acts as the negative plate of the capacitor. Another aluminum foil without the oxide coating is used to make electrical contact between the paper soaked with electrolyte and one of the terminals of the capacitor. In this figure you can see a variable capacitor. So now we will discuss the principle of a variable capacitor. You can see here a shaft, and to that shaft several layers of the plates is connected. All are in contact. Even though there are several plates, all are in contact and they form one plate of the capacitor. And when we rotate the shaft, these plates will also rotate. So they are called rotors. And you can see fixed plates here they are called stator. It also contains several plates, but all are connected together to form the second plate of the capacitor. So rotor acts as one plate of the capacitor and stator acts as the other plate of the capacitor. When you rotate the shaft, these rotor plates will move inside the stator plates. So when you turn the shaft to one side, the rotor comes out of the stator plate so that the common area shared between the rotor plates and stator plates will reduce. That will reduce the value of capacitance. And if you rotate the shaft to the other side, these rotor plates will go inside the stator plates so that the common area shared by them will increase, and that will increase the capacitance. So when we rotate the shaft, the common area shared between the rotor and stator plates can be varied, and in that way we can vary the capacitance. So that's all in this video. Thank you.